So yeah, let me give you a disclaimer. This talk is terribly underprepared, but it has the advantage of being short, so maybe not everything is that bad. Yes, I'm going to talk a little about Horseshoe homology today, and when preparing this talk, I decided to, maybe not wisely, to try and compute some example which is related to our general discussion. So I wanted to compute homology of the three loops over sphere, over a sphere of some dimension. I will give definitions in a moment, but let me just state that there is a theorem of Goodwill, if I'm not mistaken, that relates this homology to
L or C?
this is L.
Okay.
Yes. It relates this homology to Horseshoe homology of well, let's say with integer coefficients, and there will be algebra, DG algebra of singular chains over more loops of on sphere. Put coefficients there. Well, something like that. So I wanted to compute this thing, and original Day's paper gave me an idea to do this simplicity, which might not have been the best of ideas, but I did try to do that, and I will probably tell you a little something about this, and maybe you'll help me to regain my sanity, because, well, I couldn't.
Probably we want to find a way
to not do this.
Yeah, to find some cheap way to.
Yeah.
And what is this
Well,
algebra?
Which one? This one?
Yeah.
Well, I won't go into details now, but yes.
So in general,
Yeah.
the answer is something like this. I want to compute homology of a free-loop space. And this theorem of Goodwill-Jones, which we'll see eventually, says that it's the same as Horseshoe homology of some DG algebra. What is it? It's going to be the DG algebra of chains on some topological group. This topological group is supposed to be base loops. But in order to get a kind of good group multiplication on base loops, you need a model for it. And there's a particular model called Moore loops, because you have problems with parameterizations and composing. So it's a model for base loops as a group.
Yep. Right. So let's define Horseshoe homology. Let's fix a commutative ring which will serve as our ground ring.
But is it true that any associative monoid is not equivalent to a genuine group?
I have to think about that. No, I think it's a little different. You have this group completion.
Yeah.
So I think the statement is more like, it's called group-like. So basically, does it induce a group on pi 0? And then there's this theorem of Stashev that up to homotopy in some smart sense, connected pointed spaces
Yeah.
are the same as topological groups. And the equivalence is given by take base loops in one direction and take classifying space in the other direction. So this is called looping and and there are various ways to try to make this precise. One is this.
But
Another way is
yeah, what you talk about that you have equivalent model for your group like monoid given by some base loop space. But I'm asking either a model for this thing being actually a topological group.
I think there's always a strict topological group that represents it.
So this genuine inverse?
No, I mean this is like some Quillen or affinity equivalence between these things. So certainly there's a functor from topological groups, make them sufficiently nice, to pointed spaces, which that functor is take classifying space. And the claim is that this fits into a kind of maybe zigzag equivalent equivalences, where the equivalences of topological groups is not homeomorphism, but like weak equivalence. So for instance, the real numbers is contractible under this. And there's a simplicio version of this to the con also. So I mean, you can prove this kind of theorem using simplicio sets as your model of pointed spaces. And then you can write down like an explicit simplicio group that models the space of space.
This will be really
simplicio group. Yeah.
Okay.
Yeah.
It will be strict.
Okay.
Yeah. And then if you have simplicio group, and then you take its geometric realization, it will be really a topological group.
Yes. So let K be a commutative ring, and consider an associative unital K algebra, and the maps di going from n plus 1 tens of power to n tens of power, which do the following. It just di of this thing is for I less than n, and dn is just well, and these maps satisfy the familiar, I suppose, simplicial identities. And this allows us to define a differential which will denote by B. Which is defined simply as this. And you can check directly that composition of these maps is equal to 0. And that way we get a chain complex like this, and homology of this chain complex are called Horseshoe homology of the algebra A. Yeah. Well, we can define them more generally for well, we won't need this probably, so let's not waste time. Now, formally let's say nominally the topic of my talk was Horseshoe and cyclic homology. So I will also define cyclic homology, although I won't get to using it today. But it serves the same purpose, only in the equivariant case. Well, anyway.
There's an explanation of where this comes from, right?
Explanation for what?
Where this complex comes from. What does it mean?
Well,
So it's also Tor. This homology
I
is
mean the
Tor of the diagonal bimodule with itself.
yeah, but
So the complex is important, but it's important because this particular complex has extra symmetry. But if all you care about is this homology, then it's just Tor from A and A over A op tensor A.
yeah,
And there's a standard resolution of A, the diagonal bimodule, and if you use that to compute this Tor, you will discover this complex.
okay.
Okay, so that's a complex.
Yeah, but just a question. But then is it useful for the computation purposes? This,
Yes.
or, I mean, it's just I have a very
What it means is that this because it's not just homology of this particular complex, it's Tor. That means you can compute it using some other resolution of the diagonal bimodule, which is maybe smaller.
I see.
And this complex is big, but it has an advantage, which is that it has a certain extra symmetry, which is this big B operator.
Yeah. Okay.
So anyway, that's a comment.
Yeah. Okay. Thank you. Now I'm thinking what I'd rather do next. Well, let's just at least define cyclic homology. So,
Are you going to define big E?
well, I mean, I wasn't prepared to do that, but yeah. As I said, I got I kind of carried away, maybe in the wrong direction. Yeah, so maybe we should discuss this actually, since that's mostly what I've been doing for some time. So. Yes. Yes, I just erased the thing that I wanted to compute, and it was the following. And this thing, well, I mean, more generally, if you want to compute the Horseshoe homology of a DG algebra, we'll have, we'll get a, how to say it, bicomplex, and to compute its homology, we'll need to consider the total complex, and well, let me just briefly sketch my let me briefly sketch the strategy that I had in mind, which is probably a very naive one, and that's the reason why it didn't work. Just this is just kind of what I picked, I guess, from Regional Days and Goodwill's paper. Maybe it was well, anyway, let me just say this. I want to try to get a handle on this algebra to then compute its Horseshoe homology. And there is a simplicial model for this thing, and first start with a simplicial set X, which has the n-dimensional sphere as its geometric realization. And well, there are different ways that you can do this, but I think the simplest one, and the one which is useful for the purposes I have in mind, is this. Which means basically that you have you have the vertex in one vertex, which and of course it's the generis up to dimension I suppose n, right? Oh yeah, and here you'll have all the what's the compact way to say it? Well, you will have this this base point, and also all the simplices of the form where and so you have the collection of the vertices, which is non-decreasing, and you should have so this collection should contain all the vertices. Otherwise, it will just be a degenerate simplex because we quotient out.
I don't understand this description of what?
This
What are k simplices of this sphere?
Well, I'm describing
K simplices
k. Okay, well,
yeah, I mean it's easy to describe through Bergkamp correspondence, but I don't I can't read how you parameterize simplices which are both n.
Which are what?
What is written here?
Yes, well, up to dimension n, you'll just have
yes, and above.
And above you will have all the so the simplex.
Your answer does not depend on k. That's why I'm asking.
I'm sorry. This should be because sorry, should be k. Thank you. And I also said that these vertices should contain all of the.
When you call them vertices, is just numbers.
Yes. I mean, from 0 to 1. So there should be every number from 0 to 1,
Okay.
and it should be non-decreasing.
Okay.
Well. So yeah, this is just a shorthand for that. So, I suppose it's quite suggestive. Right, and this is kind of so yeah, we get the simplification model for the sphere. Then.
But you, I'm going to write down base maps.
Do you want me to?
Really, I don't understand why we trying to describe Horseshoe homology through some simplicial stuff.
I mean, it's just I'm how to say it? I'm talking from the position of ignorance. So it's just I tried like the first thing that came up. And well, I tried my best, and probably it wasn't the best idea, but
So I think the first thing to do. So for simplicity, we could take Q coefficients instead of Z coefficients.
Okay.
That's a valid thing to do. And then we could ask, what is the homology of the base loop space? And how do we compute it? Just the homology. Forget about the algebra structure for a minute. And there's a general statement about homology of groups or of H spaces that they look like some kind of polynomial algebras on odd and even generators. So we need to find the generators. And I think there might be a difference between even and odd. But there's an obvious element, which is if you write down the base loop space of Sn. Go ahead, write it down. Loops Sn, omega Sn.
Okay.
Look at what is the first non-zero homotopy group of this. You're mapping in spheres of low dimensions.
Right.
And because of the loops, if I map in the K sphere into the loops, that's the same as mapping in the K+1 sphere into Sn.
Right.
By adjunction. So loops
So it should
base
be.
maps from S1, and so you can move the loops over to the left as a smash. And SK smash S1 is SK+1. Do you want me to write that?
Well, if I understand you correctly, you mean that the first non-trivial homotopy group should be n-1?
N-1. And that corresponds to the first non-zero homotopy group of Sn, which we know is the
No.
integers.
Yes, yes.
So we know like what the first non-zero homotopy group is, and therefore we know what the first interesting homology group is by Hervé-Witz.
Yep.
So we also know Hn minus 1. Right? Okay, and then what? I'm guessing, I think, that generates the algebra. The class in there generates the algebra.
When
we-
n is odd.
You think there's an additional generator when n is even?
Yes.
So what is it?
I don't know. So this there should be a lot of elements from spectral sequence point of view, but I could not express it geometrically like the first one.
So there's this Koszul duality statement that for a simply connected space, the homology of the base loops is Koszul dual to the cohomology of the space. And I thought that I only needed one generator to make that work.
So are we working with rational coefficients or with integer
Let's do
coefficients?
rational coefficients.
So maybe with rational coefficients it doesn't matter whether it's odd or even, because I believe that for even dimensional sphere you would get some torsions, right? Which maybe I'm.
I need to compute something.
Okay.
But for n odd, it's sure.
Yeah, for n odd, for instance, for n odd, this is true. It's generated by this. And then you can show that this, in fact, this DG algebra, at least this DG algebra is quasi-isomorphic to its homology. You just choose an element representative for this homology class that will define a map of algebras, and then you will get the quasi-isomorphism. Then what?
Then we have to avoid Horseshoe homology of the polynomial.
Of a polynomial algebra, which is not hard. So just a second. continue, and we'll think about what the answer is for this example.
Yeah, well, okay.
But I think writing on an explicit simplicity model will produce a very big complex. And
Yeah.
you won't be able to see what's going on there.
Well, I did try. So yeah, well, if I'm to continue, the next step would be to consider Khan loops over this. And these will be free groups, and you can count the number of generators. This just well, I suppose I should write it down at least.
So what our nearest goal?
Well, I'm not sure.
Do you have the formula for big B?
For big B, no, I don't think I have.
Okay, I can try. I can try to explain cyclic homology. Or do you have some definition for it?
Well, I can define just. I can just give the basic definition of cyclic homology if it's.
Okay, and what is written
Here.
Yeah.
So I've taken Khan loops over this simplicial set. Do you want a definition?
Everybody knows this.
No, it might.
Specific simplicity model for the base loop space.
Yeah,
Okay.
it just might be beside the point actually. So,
Okay.
so let me just give the definition of cyclic homology, and then we'll see. So there's an action of cyclic group on of order n+1 on n+1 times the power of a. Just let's call it generator T, and then T acts on elements of times the power by permuting elements. Yeah, so one then defines say I have this T operator. We will also need this one, which is called a norm operator. And also there will be one, I erased it already. So if you remember, we had this thing in the definition of Horseshoe complex. And we have something very similar, B prime. It just doesn't have the last summand.
B prime is a cyclic, right?
What?
B prime is a cyclic.
B prime.
So it's just making your complex you start with standard complex, which is a cyclic.
Yeah.
I understand. Notation correct.
Well. Yeah. I think I think you're right. So this bunch of maps satisfy the following relations. And which we define a B complex and so on. Yeah, so here we also added the minus sign, so the squares will anti-commute. So we get a bicomplex, and the definition cyclic homology of A is just a homology of the total complex of this bicomplex, I would call it.
Sorry, can you say again what this action does again?
So what?
What does this action do?
It cyclically permutes the elements.
Okay, because your ring was commutative, right? Because so it doesn't matter the order of tensor.
Come again?
And does that matter that the order of tensoring because the ring was commutative? So
Not necessarily.
No, ring is commutative, but tensor algebra or vector space underlying the algebra is.
The round ring K is
So yeah, this is the definition. I suppose. Big N.
That is the number.
No,
So- yeah.
So I would think of this not so much as a definition, but as a formula.
Well, yeah.
So there's a more intrinsic definition, or kind of more moral definition, which I can try to explain.
Yeah.
They're not exactly prepared, so it'll be a bit rough. So I can sketch the whole idea, but I'll get formulas not quite right. Let's see. Give me a minute, I'll try to find a reference which has the formulas. But maybe then, did you have something else you wanted to add, or maybe we should take a break for a few minutes while I do this?
Well, sure, we can take a break. Кто не знает, как остановить трансляцию?
Там, кажется, да, есть опция перерыв 10 минут. Или нет? Ну или можно остановить, просто там продолжить.
Ну вот я в прошлый раз так пробовал делать, да, в общем там...
You want sketch
окей.
Ну или можно и остановить.
some general
Я думаю, если возможно свет включить, то оно все за...
Yeah, I want to explain what it really
Или можешь просто выключить этот камеру и это, а потом
Это.
включить.
Вот так.
So it's this extra symmetry. So here, there was a simplicial object, a simplicial module. There were face operators, and also degeneracies where you just stick in a 1. So we also have these sort of degeneracies, which we insert a 1 in the appropriate place. But there's additional symmetry like this. So the sign has to do with what you put in once you've already totalized. So just at the kind of simplicity level before you take alternating sums, there's just some symmetry like this. And then there are, you could ask, so this is in degree, is this n? I think it's n, and this is n.
So on a spatial level, it's just the permutation of the faces with the simplex.
No, it comes from a simplicial circle.
Okay.
But anyway, in degree n, there's this operator which acts as a cycle. And then you can work out the relations between the faces, the degeneracies, and these extra symmetries. So you know there's the usual simplicial identities, and there's some additional ones involving these. I will just give an example, there's a list of them. But as an example, you have, for instance, a relation like this, which you can check. And then some more. So there's a complete set of relations. And this comes from, you have the simplex category, and there's a bigger category which contains it, which has some additional generators in it. So this is called Home's cyclic category. And so there's a topological definition of it, and there are combinatorial models of it as well. But the original topological definition was the following. It is, so the objects of lambda are, they're usually written sharp brackets in, so it's the same objects. So this corresponds to the usual ordered set. But now instead of thinking of it as an ordered set, you think of it as a cyclically ordered set, I think. And is uniquely of the form, so there's a kind of decomposition of it into two pieces. Phi G, where what? Where phi is one of the usual simplicial maps, so it's order preserving. And G is an element of the cyclic group, driven by some Tn. Okay, and then you work out some list of relations. And the basic fact,
it is, you can decompose it in unique form. You ask for phi map, say, 0 to 0. So, I mean, it seems that objects in this cyclic category are...
they're the same as in the simplex category. You can think of them as like...
as points over circle,
circle.
second circle, and you have, instead of monotone maps, you just don't allow them to intersect each other. It's just like...
So there's a cyclic order rather than an order, because there was an interval and you glued the ends together.
Yeah, and it seems that acting by cyclic group, you can assume that phi maps, say, 0 to 0.
I don't remember. So we just copied this statement from Loday's notes.
Yeah, so the, I think the argument is that, for example, if we take some big ordered set and then we like at one point in it and we can embed it two ways, and these ways can be transported one to another by cyclic order preserving rotation of the circle. So this the condition is not yeah.
So you think phi has to preserve 0?
Maybe. I mean it will fix it, but can I just say that like these are the cyclic order preserving maps, whatever that means?
There's a way to say it like this, but I remember it being a little more subtle than you at first think.
Okay.
So I'm not prepared to. But there's a very nice discussion of this in a paper of Dieterhoff and Kopranov. They kind of very carefully say what is a cyclically ordered, what is the category of cyclically ordered sets. I mean, they have many papers, but you can look for the one that has maybe the word paracyclic in it. So there's an analog of this where these things, instead of having order m+1, have infinite order. And then this category is a kind of quotient of that. So that's one way to present it. So this is, anyway. I don't remember and I don't have the best references to hand. So there is an extension of the simplex category, which takes into account some extra finite order automorphisms in each degree. Then a cyclic object is a pre-sheaf on that. So you look at cyclic modules. And the claim is that if I had a DG algebra, then sending n to an+1 with these space and degeneracy maps and this cycling gives a cyclic module. Okay, so that's one claim. So this is so this d plus n tau give a cyclic module. So why is this interesting? So I don't know if this is theorem, proposition. I don't know who first observed this, but I know one place it's proved is by, in a paper of Dwyer, Kahn, Hopkins. They do a few interesting things in this paper. So I'll just say a bunch of things they do. It's probably not all stated in the same thing. So you know that you can introduce a notion of weak equivalence between simplicity sets, and then that's a model for homotopy types. So you could ask, is there, what are these cyclic sets modeling in topology? So the claim is that the pre-sheaves on here so I could restrict along delta, so there's a forgetful functor. Like this. So this is a model for topological spaces with Poisson equivalences. And what this is S1 topological spaces. Topological spaces with an S1 action, and the maps are equivariant, and the underlying maps on homotopy groups are equivalences. So this is the claim, that this is equivalent equivalence. They construct it. So you show that if I take the geometric realization of one of these things, then it acquires the action of a circle. And part of what goes into proving this is that you have to compute the classifying space. So for any category, you can take its derivative. Lambda lambda and lambda op turn out to be equivalent, it doesn't matter much. So you can take the nerve, that's a simplest set. You can take its geometric realization. And the calculation they do is that this is KZ2. So therefore, it's has the homotopy type of classifying space of the circle. And so what's going on here actually is that there's a Girton deconstruction that takes functors and turns them into fibrations. And so if I have a functor like this, I can perform the Girton deconstruction and get a fibration over the nerve of lambda op. That will be a space over BS1. And then by looping, I get an action at S1. So idea is given this, the Girton deconstruction gives a it's probably Cartesian. So let's call this, I don't know what to call it. Just call it F. And this is what you see. Something like this. And then I will take the nerves. And geometric realizations. Okay. And so now this will be a space over a classifying space of the circle. And looping we'll say that, well, the loops at the base point will be the circle as a topological group up to homotopy, and therefore will act on the fiber.
So what is phi? You construct some category over lambda, by F.
Yes.
Right?
And it's, what is it? It's such that this was set, right?
Uh-huh.
So it's actually a category fibered in sets. So the fiber categories are discrete. They're just objects with no interesting morphisms. So what is it? The fiber over an object.
No, I just maybe I don't understand what are morphisms in.
I tell you. I'm going to tell you.
Uh-huh.
Okay. But I'm going to tell you kind of fiber by fiber what it looks like, and then how to go from one fiber to another.
Yeah. By the way, the fiber is over object X is what?
Yes. So the fiber over that is just the value of f at x.
Okay.
It's a set.
Okay.
Okay. But if I had a morphism, not in, if I had a morphism in lambda, what lies over that? So in lambda op, that would be a morphism like this. So I might be confusing the order. And I apply f to this, so I get a map like this. So I think the morphisms are something like, so the objects are maybe just disjoint union of all of these things. And then there's a morphism from one object to another if there's a morphism down here, which lying over it has an induced map on fibers.
Yeah, I'm still confused because we want to obtain some category phi that is distinct from lambda, and okay, I see what fiber looks like, but I don't
The
understand
morphisms,
the
maybe the morphisms you should think of as pairs. You can write them as pairs.
So it's
Where-
element in f of x.
And a morphism here, and a morphism here, and then a morphism here such that on the induced f phi, it takes an object from here to here.
Okay.
So I don't remember exactly, but it's something like this.
Okay, it's reasonable. So objects of phi are a pair of object in lambda and element from f
Yes.
that's object. And
And then
morphisms are such thing that maps this chosen value to the chosen value. Okay.
Okay, and then, anyway, this is a rough idea of how you get a space with a circle action out of this. So this calculation is the fundamental calculation. And then, right, then what? Right, so now we're studying a linear version of this. We're studying this Horseshoe complex, which is a cyclic object, comes from a cyclic object. It's lambda op mapping to modules, not just to sets. And so a cyclic module lambda op 1. This gives rise to a local system. Also by a kind of gradient construction, a local system on this classifying space. I'm just going to write it as d lambda without the nerve and the geometric realization. It gives rise to a local system here. So I call this n dot. Then we'll call the local system script n. And which is the same by looping on the fibers. A local system on a classifying space is the same as a module over chains on the base loops. So we get chains on base loops acting on a fiber. So this turns out to be the geometric realization of this original object. So that's the alternating sum. This is the thing whose differential is this alternating sum. Okay. And there's an explicit formula for this. So you can do work. So first of all, this was a classifying space for the circle.
So can you repeat your message again?
Okay, so let me get maybe a more general statement. Suppose X is a connected pointed space. Then I claim proposition that the kind of derived category of local systems on X. So you can look at like the derived category of complexes of sheaves with locally constant homology sheaves. I claim that this is equivalent to DG modules on chains of the base loop space. And the way this works, heuristically, is if I have a local system that has a fiber, and because it's locally constant, I parallel transport along loops. So if I take a loop, it gives me an automorphism of the fiber. So I get an action of the group of base loops on the fiber complex. And that factors through the action of chains. So this can be made formal in various ways, but in the end, I mean, this is the statement. And if you apply this to X, this classifying space, then loops, by this calculation, this will be, as a topological loop, homotopy equivalent to the circle. So I'm getting an action, a local system on B lambda gives me, up to homotopy, gives me an action of chains on the circle. And chains on the circle is something very easy to understand. So chains on the circle is a formal DG algebra. It's as a DG algebra, quasi-isomorphic to its homology. And its homology just has a single generator, the fundamental class, which in this Hochschild story is traditionally called big B. So big B has homological degree +1. And is square 0 because there's nothing a homological degree to. Okay. And so this geometric realization of this cyclic object should have an action somehow of this B. Up to homotopy at least. It might be like an A infinity action. But in fact, people have worked out a formula for it explicitly. So Kohn first did this. So, so a formula can be given for B. And in terms of what? In terms of these degeneracies, it's not surprising that the degeneracies appear because B is going like this. It's homological degree 1. So in terms of degeneracies and cycles, so we have these cyclic permutations. So there's some formula for B in terms of this data. So I can give references, but I think it's also in the Bible. But he probably doesn't explain why it comes from the circle.
Yeah, the formula actually is in terms of bicomplex, which.
Well, I want to explain where the bicomplex is coming from. So I think the right way to think of it is because the Hochschild complex is really not just a simplicial module, it comes from a simplicial module or from a cyclic module, then, at least in some homotopical sense, it's acted on by the circle. And by a kind of miracle, that action can be made kind of strict. You can write down a formula for big B.
Yeah, but I don't understand. The big B is something which comes from bicomplex and.
No. This is what it is, I'm telling you. It doesn't come from the bicomplex. It's an ingredient that goes into the bicomplex.
But how you give a meaning to? So this is not some strict action. It's some you mean infinity action.
A priori, it's an infinity action. A posteriori. So like the way I explained it in some very homotopical way.
Yeah.
But in the end, you can show that all of this is actually equivalent to something strict for which you can write down a formula. And the formula, I can write down the formula for you if you want. It's not too bad. So just
Yeah, I mean my confusion is related to the fact that this bicomplex that was written is not quasi-isomorphic to Horseshoe complex, right?
what bicomplex? The one that he wrote down.
Yes, where you have
But-
B by B
Yeah,
prime,
but,
B prime.
yeah, but we haven't even got there yet.
Okay.
Forget about the bicomplex. That hasn't entered the story yet.
Okay.
So this big B is different from this B little prime. What
Yeah, I understand. I mean, big B has a formula in terms of bicomplex.
It is, so here's the formula for big B.
Yeah.
Forget about bicomplex.
So this is.
Forget about bicomplex. We're not there yet. We don't know what it means. We had some ridiculous formula that was totally meaningless. I'm going to tell you what it means. Okay? So first of all, big B means what I said. It's an action of a circle.
Okay.
Okay? And by some miracle, it can actually be computed. A priori, it was going to be some A infinity formula.
Okay. We have this formula. How to interpret it as an action over Horseshoe complex?
So the claim is that this works, in fact, for any cyclic module.
Mm-hmm.
And that this is the formula. So here's the Hochschild complex. I want to write it not with the arrows going
My question is, what we mean by action?
Well, it's a DG module, so let me tell you exactly what it is. So if A was in degree 0.
So it's generally commutes with small b.
No, well, it doesn't commute, it anti-commutes, right? Because it has degree plus 1. So it has this. So, and what does this relation mean? It's saying the little b is the differential. B is an operator in a DG algebra, and so this is what it means for it to be a DG module. This is saying if I have B and I act on some x, and then I apply the differential in a DG algebra, if I want to move the differential past an algebra element, a sign appears, right? It's -1 to the degree of that DG algebra element. B differential applied to the module element. But this is degree 1, so this is a minus. So that's equivalent to this.
Okay, so the statement is that bicomplex that we have is actually quasi-isomorphic to terrain of shifted Hochschild complexes where vertical differential is big B, right?
Just a minute. So we'll see where it comes from in a sec. Okay, so what do we have now? We have a complex. It has a circle action. By circle action, I mean action of homology of the circle. That's reasonable, because if I had a space with a circle action, then this would act on the homology of X as a DG module. Now, the circle's a group. This is not just a DG algebra, it's an augmented DG algebra. Right? Because there's a map from the group to the trivial group. So there's an augmentation. Which means I can take homology with respect to that. Right? So I can take coordinates. Okay, so definition of cyclic homology. So the cyclic homology, let me say, cyclic chains. So let me tell you what it is as a complex up to quasi-isomorphism. The cyclic chains of an algebra A, and you can do this for a DG algebra by totalizing, is, so let me give you the invariant one. It is K, the trivial circle module, tensor over the circle with the Horseshoe complex. Did we have a name for the Horseshoe complex? I don't know, I think people would know what to call it. This one. But considered as a circle module with respect to big B. So this is the derived thing. And now, here's an exercise. This is where the double complex comes from. Notice, I mean, what is this? This is coinvariance. If I palmed in from K, that would be invariance. This is coinvariance. And coinvariance is taking a quotient. So this is like equivariant homology. This is S1 equivariant homology. It's the algebraic version of that. Derived coinvariance like this is how you take a quotient of a group acting on a complex. And then exercise. And I can kind of indicate how to try to do the exercise. Write a formula for this complex. Write an explicit complex. Write an explicit complex using. So how do I compute tensor product of DG modules? I need a cofibrant resolution. It's kind of the DG version of a projector resolution, right? So I need a cofibrant resolution of this. So DG module resolution. K tilde mapping to X. And there's a very minimal way to do this. If you just follow your notes, you will find the same thing that everyone in the history of this subject has ever found. And if you put it into the tensor product and work out what you get, you'll get the same thing that, is it Ilya?
Vladimir.
Vladimir. Who's Ilya? He's also on the list somewhere. Okay, so the same complex you would get from the double complex that Vladimir wrote is what you would get if you use the kind of standard resolution here. So what should the standard resolution look like? Well, it starts out, you kind of think of it like this. So I have augmentation, right, which has a kernel. Which is B. What is B? B is K shifted by 1. It's actually, again, the trivial module, but shifted. And so then I take the shift of the augmentation, and that has a kernel. It's B shifted by 1, so it's K2, and so on. Okay, you go on like this. And in the end, what you find is that K tilde as a module is kind of semi-free. So if the underlying graded module is free, it looks like it has a generator in degree 0, a generator, let me get this right. Right. It will be degree 2, degree 4, and so on. With differential, dxi will be, I think, bxi minus 1. So it's semi-free in the sense that the underlying graded module is free on these guys, but it has this differential. And you can check that that's a resolution, and kind of by the way I constructed it, it will be cofibrant. It's kind of cellular. So if you use that to compute this tensor product, you'll find the kind of standard complex for cyclic homology. And another notation that's nice would be, if I had any circle model, I could take its homotopy covariance.
Yeah, but a small remark that in this construction we obtain not a bicomplex which was written, but a smaller model, right? Which looks like train of shifted Horseshoe complexes with vertical differential big B.
I don't remember what that bicomplex was.
There was small b prime.
So there are a few different complexes in the literature to compute this. Some of them work in characteristic 0 only. I don't remember. I can look at it in Bible, which one this is. But the thing I wrote down, I think, works universally.
No, actually, the problems in this story about UN characteristic 0 or not starts when you relate this to the RAM complex.
Not only that. There's a. It has to do partly with the homology of the cyclic groups that appeared.
No. For this fact to get from bicomplex to smaller one, which I just described, you need to know only that B prime is acyclic.
So there's Ziegen's double complex. I think is this the thing you wrote down, or did it look like this?
Yeah.
Okay. Versus what? What is the alternative? Okay, I see. So no, in characteristic 0, they just, you can kind of factor out these terms by cyclic groups to make them smaller. I don't remember for sure, but I thought that this does pretty much give the. Yeah, I don't know why there's a B prime. Just a minute. I thought I convinced myself at some point that this really did give this Siegen double complex. But I don't see why.
No. Your construction directly gives you a smaller quasi-isomorphic. You obtain say bicomplex which have a support in first quarter plane above diagonal. And
I see. Okay. I should say though, there are a few things that come out of this from this point of view that it's like other constructions that become kind of very natural. So one is, this was co-invariance. I could have also done invariance. And this is less important in string topology, but it has a name, it's important in general. It's called negative cyclic homology. So you could hom out of this resolution instead of tensor with it. And you get something called negative cyclic homology. This is what corresponds to the Hodge filtration on de Rham homology somehow. And what? The other thing is, because this is circle equivariant homology, there's a...
So this corresponds to derived Holmes from K over S1 to chains. Okay.
So there is such a thing in general that's important. We won't need it so much for the string topology, because the topological meaning of that would be homotopy fixed points of the circle acting on your space, and that's kind of somehow less interesting than taking the quotient in the case of the free loop space.
As far as I remember, or at least over Q,
they're very different.
They different, but fixed points are, for example, of free loop space are just your space, your starters. So
That's
it corresponds to loops which are constant.
I'm skeptical of this statement. It gives the wrong answer for the homotopy fixed points, not like that would give the wrong answer, I think.
Okay, I thought that over Q is the same thing.
Right. So I guess there's one more thing, which is this so-called Gizen sequence. What is this? So if say this in two ways. So there's a topological meaning and then a purely algebraic construction. So suppose I had a circle acting freely on X, so that the quotient was the homotopy quotient. Yeah. Then what? And this would be a circle bundle. This would be a circle bundle.
One long character sequence for the homology.
Yes. So indeed, if I look at the so the fiber is one-dimensional, and so if I try to write down, say, this Serre spectral sequence, I would just go along the exact sequence. So the spectral sequence for homology is just a long exact sequence. And in that long exact sequence, you'll see something like the following. You'll see HI of X. I'll have the quotient. So H1 of X minus 1. And what? And I'll have a connecting map, which I have to think in which order this goes. Is it -2 or +2? Just a second, I think. Yeah, I think it must be -2. And then this one, I think, should be -1, I believe. So this is called the periodicity sequence, or sometimes SBI sequence. Gizen sequence is probably what it's called in topology, but in cyclic homology it's called this. And where it comes from in algebraically is you could look at we can look at the cohomology. So that's cohomology of BS1. So this is cohomology of BS1, which at least the cohomology is polynomial algebra in a generator U of cohomological degree 2. So homological degree -2. Remember, DG modules of the chains corresponded to local systems on the classifying space. This would be the true local system, so its cohomology would just be cohomology of the classifying space. You can also compute this explicitly using this resolution. The differential will end up vanishing, and you'll just get a generator in every even degree. Okay, so this therefore acts on the homology, because this is endomorphisms with K and tensor with K. So this will act on this inner circle module. And so that gives, for every circle module, I have the quotient map. And then I have this generator U, which maps to what? I guess -2 like this. And is that right? Yes. And I think I must have must be right. Yeah, that's right. So this ends up being a exact triangle, and you take the long exact sequence in homology, and this is the kind of thing we get. Okay. So I think that's all I can say at the moment without having prepared better. We could try to do a calculation. So the only calculations that I know how to do are when the algebra is commutative in some sense, or maybe if it's a group algebra. So I can mention, I'm kind of not giving you detail, I'm kind of just giving you a table of contents for everything. How to do a calculation. So there's something called the Hochschild-Poisson-Rosenberg theorem. There's some version of it in general, but this version is best in characteristic 0. So let's say Q. Suppose my K is a Q algebra. And suppose A is either smooth commutative or more generally it could be what do you call it? Quasi-free connected. I'm not sure that that's actually important. CDGA. So commutative differential graded algebra, commutative in the Cazul sign rule sense. And quasi-free means if you forget the differential, it looks like a kind of supercommutative polynomial algebra. And connective means homologically non-negative. I'm not sure how important that is though. And then in this case, the statement is that the Hochschild homology of A is equivalent to, it's not exactly wrong, it's something funny. It is, you take the Kähler differentials, and normally for the Braun complex you would put them in degree 1 homologically degree -1. Here you actually put them in homological degree 1, so you shift them down. And then you take sim of that. So if A was smooth commutative, this is concentrated in a single degree, and you're done. The differential is 0. If A was one of these quasi-free CDGAs, then it still inherits its own differential. This would have some differential on it, which in the smooth case would be 0. So this is a quasi-isomorphism. So let's try to apply this in some example, like the example you were considering of base loops. So I think we can do the 3-sphere. The circle's a little bit funny, just because the circle's not simply connected. Maybe that's fine, actually. We could do this. Well, okay, let's do the circle and the 3-sphere. I'm still confused about the 2-sphere. So the circle, if this is my space X, then the base loops of the circle as a group is just integers. It only has pi 0 because the circle only has pi 1. Okay, and then what are our chains on this? This is a discrete space, right? So as an algebra, this is it's just a group algebra. This is KTT inverse, where T is, say, a generator of integers. This is the group algebra. So we're actually for the Hochschild homology of the group algebra. And that's, via this, easy to compute. So, let's call this A. It happens to be commutative. This is kind of accidental. In general, this kind of chains in a base loop space, there's no reason for it to be quasi-isomorphic to something commutative. Right, so this is free of rank 1, right? This is A times the Durand differential of T. This is just the affine line minus 0. Right, and so what we find is that HH0 of chains of base loops in a circle, it is Laurent polynomials in degree 0. So that's the sim 0 term of this. And in degree 1, it is also basically Laurent polynomials, but the natural generator is that times this. Actually, it's a little bit better. Doesn't matter. It's kind of better to choose dt over t as a generator sometimes. It doesn't really matter. That's a choice, but for some reason, that's the natural choice. So there it is. That's the calculation for the circle. And for the 3-sphere, and once you see the 3-sphere, you can kind of do all the odd spheres in a similar way. So I think if I'm not mistaken, that the chains in the base loop space is formal. And just a polynomial algebra and some generator, it's that generator which comes from the first non-zero homology group, which is in degree 2. So this is degree 2. And this is one of these quasi-free CDGAs. The differential is actually trivial because it's formal, but it looks like a graded polynomial algebra. And the DG Kähler differentials look like A times dC. It's always like that for a polynomial algebra. And so this means what? It means HH0. So this already has degree, I'm going to be interested in the following. So this is 1 shifted by 1. I'll have A, I'll have omega 1 shifted by 1, and then I'll have higher symmetric powers of this. So let's think about that. So I'll see like wedge 2 of this shifted by 2, wedge 3 shifted by 3, and so on. But this is even. And so when I wedge it with itself, wedging is anti-commutative and it becomes 0. So there's no higher terms in this symmetric thing. That would be different, actually, if this were odd. Then these terms could be non-vanishing. And so so homology of this would look like homology of A would be actually zeroth homology of A. Because there's no zeroth homology of this, I shifted it. HH1 of A would be H1 of A, which is 0. So this is K. There's no H1 here because it has an even generator. There will be an H1 here. Because what was in degree 0 got shifted down to degree 1. This would be a K. And then HH2. So this is actually K times, is it K? Oh no, hold on. This has degree 2. So the first thing, non-zero thing here is degree 3.
Wait. D must doing something.
This is different. That's not a degree. It's not a degree. It's a. There are two gradings. There's a kind of homological degree and a kind of weight, having to do with how, is it a differential 1 form, a differential 2 form, and so on. Because of the shift by 1, they differ. So I think this still, if you look at what the universal property of Kähler differentials are, this will still be in degree 2 because this map, the de Rham differential is supposed to be a map of DG modules.
No.
It's not 3. Look, the de Rham differential is a chain map. And so it has to take degree 0. So it takes C to D de Rham C.
No. In terms of Horseshoe complex, every expression like a D of something is lying. For example, D of C lies in A tensor A. In Horseshoe.
You have a shift in the Horseshoe complex. And you do not have a shift over there. It appears later. И, например, если взять связанную алгебру, которая в степени 0, то у нее модуль кодирования дифференциалов тоже почти в степени 0.
We can compute this one by another way and compare the answer. We can also use a kind of Kazul type resolution to do this one. So I think what you're confused about is that in this version, you don't think of the drum differential as a differential. It corresponds to the action of B. And B goes in one direction and little b goes in a different direction. And it's the grading with respect to little b that is the grading in Hochschild homology. It has nothing to do with the grading of big B. So I'm going to claim that this is 0, and I'm going to claim that this is C. And then
sorry, I don't understand. 2 is for what? For which degree? What you mean by degree 2 for d psi? I said that
this is a complex.
Yes.
And I'm saying that the generator lives in homological degree 2.
If we consider a Horseshoe complex, right, then dc is a symbol which corresponds to 1 or times xi, right? That's Horseshoe constant construction. And this, by differential, should decrease
But 1 xi
right.
appears where? It appears in, so I'm going to have to take tot plus of this double complex to do this, right? So I have my algebra A. What is this double complex going to look like? Just a minute. So the simplicial thing looks like this. I will take alternating sum of face maps. So I'll make a double complex in which I'll have A0, A1, A2, and so on. And then I'll have A squared 0, and A squared 1, A squared 2, and so on. Just a sec. I think it. And I was saying it appeared in, I'm saying it doesn't appear yet. It appears in degree 3, is my plan.
Yes.
Then we agree.
Yes.
But it's because of this shift. So I'm saying here, it appears in degree 2, and then I shift and it appears in degree 3. So I think were we agreeing all this time?
this thing is generated by C in degree 2 and something in degree 3, which.
Well, I would
I
call the
prefer to call
thing in
D.
degree 3, I would call it DXC. So HH3, I'll have this.
Это ваш доклад? Он уже закончился. Закончился. Okay, I'll be back in 10 or so minutes.
Okay, but I'm going to leave. I think we're done.
Okay, well, I'll take care of...
Okay, that I'm good. Okay, thanks. So do you agree that...
Yeah, I just don't understand why you write 2 instead of 3. But the homological...
No. But it's before I shifted. This is the cotangent complex. This is differentials. And what appears in the Hochschild-Rosenberg theorem is not that. It's not differentials. It's differential shifted by 1. Here. It appears further back in the complex. And so I'm just saying that the differentials as a complex has this generator in degree 2. And then only after shifting...
Yeah. For me, a simple dr psi does not exist apart from Horseshoe complex.
Oh, I don't know. There's always Kähler differentials. That's meaningful.
So you just stated that when you consider Kähler differentials, you do there is nothing done to homological degrees, right? Okay.
No. I mean, if you do it for a DG algebra, then this is a complex, right? Take a non-trivial DG algebra.
Yes. Okay.
So let's, for example, let's say, suppose I'm trying to study the dual numbers. That's a singular algebra. Yeah. But it has a resolution, which is kt, so let's say t squared. And I don't know what to call it. I already use c, maybe zeta. Such that d zeta is t squared. Okay, so this is a nice CDGA which is quasi-isomorphic to this. And now this is A, this is A tilde. And then the Kähler differentials now. This is a DG module. This is a DG module with generators D de Rham, and that's different from this D. D de Rham T, D de Rham zeta. This one has degree 0. It has the same degree as the generator does. And this one has degree 1 in this complex. And so this is a complex, and it looks like it's free on these two things, and it has an internal differential, which when applied to this, commutes with the Rham differential. This becomes d de Rham of d of this, which is t squared. So that's 2t d de Rham.
Yeah, but I don't understand why in your notation d Rham does not change canonical.
Because Kähler differentials co-represent a functor of derivations. And if I mean, look, even classically, if I did this for just a smooth polynomial algebra, like you open up a commutative algebra book, Kähler differentials are a module concentrated in degree 0, right? And it has in it elements of the form d de Rham for each variable.
Okay.
Yeah. So that's all I mean. Yeah.
Okay.
Yeah. Okay. So I don't know. I think that's all I wanted to say. So this is a kind of method for how you could compute these things in the commutative case. For even dimensional spheres, I guess there's an extra generator, but you can still do something similar. I have to think what that extra generator means.
Do you know what it means? Meaning of the second generator. So the problem that in even dimensional case you as before have generator in the first non-trivial homology which squares to 0, and say if the first generated less than dimension n minus 1, then you have to have generated without any relations in degree 2n minus 2. That's it. I don't know geometrical meaning of this.
I mean, it's just one generator corresponds to the obvious homotopy group, and the other generator, I don't know. There must be some topological